So the next talk is called KTRW, the journey to build a debuggable iPhone. Well, hardware debugging of an iPhone is usually not possible. It's not possible with iOS devices, or it wasn't possible with iOS devices. And security research of the kernel is therefore quite a challenge. Well, with the Apple A10 chip, Apple implemented a thing called kernel text read-only regions, which is called KTRR in short. And Brendan Assad of Google Project Zero, he found a way to make a debuggable iPhone. And tonight he's going to tell us how he broke this KTRR and how he made a debuggable iPhone out of a regular production iPhone. Please give a warm round of applause to Brendan.
Thanks. Awesome. Thank you very much. I'm very excited to be here. Thank you for showing up to my talk. Today I'm going to take you along my journey to build a capability that I've wanted to have for a very long time, a debuggable iPhone. So what exactly do I mean by a debuggable iPhone? Well, in order to kind of give you the context that you need to understand this, I'm going to need to talk about something which isn't frequently talked about in public. And that's the thing called dev-fused devices, development-fused devices, prototype iPhones. These are all names for similar concept, which is a type of device, a type of iPhone that has extra debug capabilities built into it. So that's things like serial wire debug, JTAG, basically functionality that now allows you to debug the phone at a very low level. For example, doing things like single stepping through the bootloader, putting breakpoints in kernel mode and dumping registers, modifying registers, sorts of things which would be very important for Apple engineers to be able to do, but which are definitely not something Apple wants available on production iPhones distributed en masse. Now, in order to connect to these special type of iPhones debug capabilities, you need a really special type of cable, usually called a probe. Here's an example of what's called a Conzi cable. It has a special lightning connector on one end, which has a special accessory ID burned into it, which allows it to communicate with the debug hardware on the phone. It has a controller, which is the chunky part in the middle, which is able to talk the debugging protocol. And it has a USB port on the other end, which you can connect to a laptop. And on the laptop, you would typically run software. For example, there's this tool which you can find online called Asterisk. This is not software which Apple is willingly distributing. This is kind of, as I understand it, leaked code. So it's not something which is like, sanctioned. But there are people who are able to obtain this software and use it to operate these debug probes. Here's an example of a screenshot where someone was able to use a Kong serial wire debug probe and connect it to a 32-bit dev-fused iPhone. And you can see register dumps. You can read and write memory, do all sorts of really low-level debugging on this iPhone. Now, I need to say, I do not use dev-fused devices. I don't have access to these devices. I don't want to have access to these devices to do my work. That being said, it would really be incredibly useful to have such a low-level and powerful debug capability. So this is the motivation for my research project. I wanted to find some way to build a debug capability on a regular Apple certified iPhone. Some way to build my own homebrewed dev phone. And there were a number of different features that I wanted present in this homebrewed dev phone. I wanted the ability to patch kernel memory, and in particular, the ability to patch the executable code in the kernel, for example, modifying existing instructions or injecting kernel shellcode, things like that. I wanted the ability to kind of do your standard debugger features, set breakpoints, set watch points, kind of the third item that I wanted this debug phone to be capable of is I wanted it to use only standard off-the-shelf debuggers. I didn't want to use or to depend upon proprietary Apple software like Asterisk in order to operate. The next item is I wanted this homebrewed dev phone to be updatable. So I wanted to find some sort of low-level vulnerability such that if I'm going to spend 3 months trying to create this debuggable phone, and then Apple is able to patch the whatever technique was being used in the next version of iOS, and now all of a sudden I no longer am able to debug the latest version. Certainly this would be very useful. I can always diff kind of the differences between subsequent versions of iOS to still get useful information from my debugger. But I would really love to be able to amortize the development cost of this debugger over many iterations of the iOS operating system. So keep this capability alive as long as possible. In practice, what this meant was I was going to be looking for perhaps a bootloader vulnerability, maybe some sort of hardware bug, something which was either difficult to patch, or even if it was patched, it was early enough in the boot process that it would still be possible to update the version of the iOS kernel running on the device. And the final thing is that I wanted this dev phone to use only parts that you could obtain at an Apple store. So no specially fused CPUs, no special debug cables, nothing of that sort. Now, I want to mention something really, really important that happened, probably the most important thing to happen to iOS security research in several years. And that is pretty much just a couple of days before I was about to open source KTRW, AxiomX released a boot ROM exploit for all iPhones between the iPhone 4S and the iPhone 10. Now, the boot ROM exploit is actually strictly more powerful than the capability used in KTRW. Everything that I want to do in my debug phone is totally possible to do using the boot ROM exploit alone. So I want to tell you this just so that you're aware that many of the assumptions that I made going into this project really don't hold anymore, but they did hold at the time that I started this research. And I do expect that future debug capabilities and future research platforms on the iPhone will be based around the boot ROM exploit instead. So with that, let's talk about the main mitigation that makes kernel debugging on an iPhone right now both really hard to do and also so important. And that's a mitigation called KTRR. If we look back at the list of requirements that I wanted in my homebrewed dev phone, the very first item on this list was I wanted the ability to patch kernel memory, and in particular to patch the executable code. Now, normally, on most systems, this isn't actually that difficult. Once you have the ability to read and write kernel memory, you can just modify page tables, make some page in memory, read, write, execute, stuff your shellcode in there, and you're basically done. But on the iPhone, Apple has added a mitigation called KTRW. And the idea is that we have a kernel cache in memory that's been, put there by some sort of secure boot process. But once it's in memory and the system is running, Apple would really like a way to guarantee that the kernel cache gets locked down as much as possible, and any data in it which really does not need to be writable is never going to be modified. Basically, keep the guarantee that once an iPhone is booted, the code running in your kernel is exactly the code that was protected by and verified by the secure boot process. So there is some data in your kernel which does need to be writable. But there's also a bunch of data which really does not need to be writable. The most prominent example is the executable code. Clearly, we don't want that to be changeable. But there's also a bunch of other pieces of data which are worth protecting. For example, you have strings, maybe format strings, virtual method tables, the page tables that are mapping the kernel cache itself into memory. All of these additional pieces of data, Apple would really like to have them be protected and not modifiable. And that's what KTRR does. It's going to lock down all of this data that we want to be read-only as the defenders. So as far as we know, KTRR stands for kernel text read-only region. So what KTRR boils down to is it's a very strong form of write XOR execute protection. It's available in Apple A10 CPUs and later, and it provides two very strong guarantees. First is that all writes to memory inside of the region protected by KTRR will fail. But this basically is what provides kind of the lockdown guarantee that what was put there by the secure boot chain kind of stays that way and can't be changed. But there's another part to it which is equally important, and that is that all instruction fetches from memory outside of the protected region are guaranteed to fail. This is what ensures that you can't put new executable code in the kernel, that the only code that you're allowed to run is the kernel's own code. So in order to kind of understand how this works in a little more detail, let's look at an oversimplified diagram of how CPU works. So here we have the CPU cores. This is, for example, an A11 CPU with 6 cores. The little purple box in the bottom corner is the MMU. We have the highest level of the cache hierarchy is the L2 cache. Behind that is the memory controller called AMCC. And then this is connected to DRAM. Now, the kernel lives contiguously in physical memory in DRAM. And this is what Apple wants to protect with KTRR. So the first step in order to lock down this region happens on the MMU. So let's zoom in to a single CPU core. What Apple has done, as far as I understand, is basically just add a couple of registers to the MMU that point to the beginning and ending address of the region to protect. What this allows us to do is the CPU core can now check whether each instruction it's about to execute violates the security guarantees we want from KTRR. So for example, let's say the CPU wants to issue a write to a physical address outside of the KTRR region. That's fine. We can write to that memory. So this will be allowed by the MMU, and the write will go through. If, however, we try to issue a write to an address that points to inside the KTRR region, this violates the security properties of KTRR. And so the MMU will recognize this, it'll deny the write, and it'll cause that instruction to fault. Similarly, if the CPU tries to execute an instruction that is fetched from an address outside of the KTRR region, the MMU can recognize this and cause that instruction fetch to fault. But so here's kind of the new picture of the CPU cores. We have a bunch of new registers in the MMU that kind of have this KTRR protection built into them. However, this isn't the complete picture that we need in order to protect this memory. See, there are other devices that are connected to your system, all sorts of peripherals. This could be like a Wi-Fi chip. This could be like a USB stack. All sorts of things, any sort of hardware device which could issue DMA commands to your memory controller. So in order to protect against malicious peripherals DMAing over the protected region, we think that Apple has added registers to the memory controller as well that also point to the beginning and ending address of this lockdown region, such that way, anytime some peripheral tries to DMA over the secure region, the memory controller sees that this DMA doesn't look valid, and it'll just discard the write. So this is kind of the picture that the hardware now looks like in order to support KTRR. But this isn't actually the complete story either, because there's one specific edge case that needs to be properly handled. And that's when a CPU core goes to sleep for a little bit and then wakes up, what's called resetting. Anytime a CPU core goes to sleep, it's going to power down registers, and in particular, the MMU registers which store the KTRR bounds are going to lose their value and be reset to 0. So when the CPU wakes up from sleep, we need some way to reset those registers to point to the beginning and ending bounds of the lockdown region. So the reset vector is the first piece of code that gets executed when a CPU core wakes from sleep. And it does so with the MMU off. And what Apple has done is they've added code to the reset vector that basically just initializes those KTRR registers. The beginning and ending bounds are stored in these global variables. These variables, by the way, happen to lie inside of the locked down region, so they can't be modified. And once it reads those values into general purpose registers, it writes those bounds into special system registers that are used by the MMU to verify the KTRR security properties. So once this code executes, KTRR will be locked down on the MMU, and once again, you can no longer execute memory that lies outside of the lockdown region. So now that we have kind of a high-level understanding of how KTRR works, let's look at how it's possible to break KTRR. And we'll start with a few historical examples. There are two historical instances of partial KTRR bypasses up till now. And the first one came out pretty soon after the KTRR mitigation was first introduced. And it was discovered by Luca Tedesco, who's going to be giving a talk, I think, in this room tomorrow evening. So what Luca found was that Apple had left an instruction in the kernel cache that they didn't mean to leave executable, but it accidentally was. This was the MSR TTBR1 instruction, which sets the special TTBR1 register. This register stores the physical address of the root of the page table hierarchy, which means that if you're able to modify the value of this register, then you are able to supply your own custom page table hierarchy and therefore remap virtual memory onto new physical pages. So this is exactly what he did. He just chose a remapping that placed the read-only regions of the kernel memory onto new physical pages that contained a copy of the original kernel data. Now, it's important to note that KTR was still actually fully initialized at the point at which you were able to execute this MSR instruction. So we can patch read-only data, but we can't execute new kernel code because KTRR lockdown on the MMU still did occur. So what the KTRR bypass in 10.1 basically achieved was limiting what was protected by KTRR down from the whole read-only region to only the executable code. But we get a whole bunch of new data in the kernel, which is now writable. The second KTRR bypass that was released was more of a bypass in spirit than in practice, but it's definitely a very important tool and a huge inspiration for my research. So back in iOS 11.1.2, Ian Beer found that the debugging functionality in the ARM specification was actually implemented in Apple's processors and could be used to implement a full-featured kernel debugger. So if you read the ARM architecture reference manual, you'll find that there's documentation on a feature called self-hosted debugging. Basically, the architecture provides a set of debug registers, which you can access via MSR instructions. And you can use these debugging registers to set breakpoints in kernel mode and also to, by implementing exception handling code in your exception handler, you can catch your own breakpoint exceptions and basically have the kernel implement its own debugger. For example, this might be somewhat analogous to using a KDP to debug a MacBook. Now, KDP has actually been removed from the iOS kernel that's distributed on production devices. However, the debugging registers that one might use to implement this are still present, still fully functional. And what Ian found was that he could use return-oriented programming to set the values of these registers correctly in order to implement a rather full-featured kernel debugger. He built something that worked with LLDB, proved quite useful. And in particular, it was able to, by setting breakpoint, single-stepping, modify register values, execute existing instructions in the kernel in basically arbitrary order. So not native, like arbitrary shellcode execution, but pretty darn close. So I started this project of trying to find some sort of KTRR bypass by looking in kind of the places that I thought would be more powerful, find more powerful KTRR bypasses, more likely to lead to something that would be persistent across multiple versions of iOS. Where I started was looking in iBoot. I was trying to find some sort of iBoot bug in the image4 parsing and verification functions. I didn't end up finding anything there. Next, I kind of read through several sections of the ARM architecture manual, saw some interesting things about, maybe, if you have weird malformed TLB entry, or if you have weird malformed page table entries, you could do something weird with the TLB. That didn't really end up yielding anything useful. I played around a little bit with, I kind of misunderstood how KTRW worked a little bit, and I thought, maybe there's a way to corrupt the L2 cache and then bypass KTRW that way. That didn't end up really working either. So I kind of, tried a bunch of things. None of them really panned out, and I put this research on the back burner for a while. And it was actually while I was doing something totally unrelated that I happened to generate a kernel panic, which reignited my interest. So I was playing around with interrupts, and I'd managed to get a CPU core stuck in an infinite loop with interrupts disabled in kernel mode. And I got a panic message which said, panic, watchdog timer, timeout, CPU1 has failed to respond. So kind of the exact thing you would expect when a CPU isn't responding because it's stuck burning CPU cycles in an infinite loop. Eventually the system notices and panics because, there's some significant problem here. But what really caught my attention about this panic message was something much earlier in it, where it says, attempting to forcibly halt CPU1. Now, this was really interesting to me because according to what I'd read from the ARM manual, there wasn't any standard way for one CPU core to halt a second CPU. Like, there's no MSRs that you can write to. I didn't really remember any way to accomplish this. So what I figured was there's probably some sort of like proprietary interface going on here where, maybe there's special CPU control registers which are accessible via MMIO, and somehow XNU is trying to leverage those in order to halt the CPU. So this seems like pretty interesting. I'd never seen something like this before. So I decided to pull up the security engineering tools needed to figure out what was going on here. So I grepped through the XNU source code to try to find the string attempting to forcibly halt CPU. Pretty quickly came to the function ml debug wrap halt CPU, which seemed to implement this functionality. It takes the index of which CPU you want to halt. So on a CPU with 6 cores, it would be the index 0 through 5. And the actual part which halts the CPU is just right down here, a couple of lines lower. So what this does is it reads a pointer to some volatile memory from a per CPU data structure. This variable that stores the pointer to the memory is called debug wrap reg. And then the actual part of the code which halts the CPU simply consists of the single line where it writes some special debug halt value to the debug wrap reg. So this really strongly supports the idea that this is some special MMIO register. And when I was looking online for trying to find references to this debug wrap thing, I wasn't really getting any results. So it kind of really strongly suggested that, yes, this is some sort of proprietary Apple-specific interface. The other thing that kind of caught my attention was this reference to something called CoreSight. I remembered hearing, CoreSight somewhere else before, but it didn't really know what it was. Marked it as something to come back to. But what really caught my attention when I was looking through this file was a function just a few lines down called ml debug wrap halt CPU with state. This does basically the same thing as the other function, except in addition to halting a CPU, it also reads out the values of the registers on that CPU that was just halted. And the way that it does this is actually quite remarkable. So first off, you can see that there's another reference to this CoreSight thing. It says, ensure memory mapped CoreSight registers can be written. So clearly something with CoreSight is important here. Maybe it's the block of registers that contain this functionality. But the important part is this for loop right below, which iterates I over the indices of your general purpose registers. What this code does is first it's going to generate the numerical opcode for the instruction which writes the value of general purpose register xi into the special system register debug DTR. So this isn't an instruction which already exists in the kernel cache. It is just literally generating the numerical value of the opcode for that instruction. Next, it passes that opcode into ml debug wrap stuff instruction. And finally, it reads the value of the debug DTR register and writes the value into the output buffer's XI field. So this is actually really interesting because what it suggests is that ML debug wrap stuff instruction is somehow executing dynamically generated instructions. And this really flies in the face of the security model that KTRR is designed for. So KTRR is meant to ensure that, all of the instructions in your kernel cache, those are the only ones that you're allowed to execute. But here, there's some sort of interface which seems to be able to execute any instruction you want on a halted CPU. So this is definitely really interesting. Now, just because there's code to do something in XNU doesn't actually mean that it necessarily works in practice. So I basically just decided to test to see if this code actually runs. I pulled up an old kernel exploit that I'd written, and I basically just wrote and packed together something that would call the function ML debug wrap halt CPU with state, pass it an output buffer, and then dump the contents of that buffer. And what I found was that the output buffer really did look like a bunch of registers. So there's a bunch of stuff which was 0, which is kind of weird, but the value of CPSR does look correct. It actually looks like a CPU running in kernel mode. And the value of PC, it doesn't really look like a normal kernel virtual address. Those usually start with, like FFFF. But it does really look like some sort of physical address, perhaps. And with a little bit of digging into this, I pretty quickly discovered that this is a physical address of an instruction in the reset vector. Now things are really, really getting interesting, because what this suggests is that we've managed to halt the execution of a CPU core while it's actually running the reset vector, and in particular before the MMU has been turned on. Now, this is a really critical point in time for KTRR, because before the MMU has been turned on, KTRR is unable to protect the CPU from executing instructions outside of the locked down region. So, of course, what I really wanted to know was how do we use this capability in order to bypass KTRR? Well, it turns out that there's kind of a more fundamental question that I needed to answer first, which was, what exactly is this core site thing anyway? It's really hard in practice to, at least for me, to exploit something without kind of knowing a general sense of how something works. And so I basically just searched for core site in the ARM reference manual and came across a bunch of references to core site in connection with something called the external debug interface. Now, the external debug interface, it turns out, is pretty much just a different way of accessing the same functionality that Ian used in his self-hosted kernel debugger. So in the self-hosted debugging interface, you write to these debug registers using MSR instructions. The external debug interface provides kind of the very similar functionality. It's probably the same debugging hardware under the hood that you're driving, but the interface to access these registers is via MMIO rather than via executing MSR instructions. So this means that basically the functionality that is necessary to build a kernel debugger is still there, even though the ROP gadgets that Ian used to activate it are taken away. The memory mapped interface still exists. And in fact, this isn't even the first time, not even close to the first time, that someone has tried to use debugging registers in an ARM processor in order to mount some sort of privileged attack. Xinyu Ning and Fengwei Zhang presented an attack at MOSEC 2019, where they basically were able to leverage these same debugging registers on Android phones to break the protection of the secure world. So they were able to make one CPU core debug another CPU core, make that second CPU core execute instructions to enter the secure world at EL3, and then also make it execute instructions that would cause it to read and write memory in the secure world. So just to summarize kind of the key concepts behind the external debug interface, it is an on-chip debugging architecture. It provides per CPU debug registers, which are accessible via MMIO. The actual interface itself, how to use these registers, is really extensively documented in the ARM manual. It talks about, what the names of all the registers are, the offsets of them, like how to program the registers in order to do things like set breakpoints and watch points. So I'm not going to go over all of that right here. But what I will say is that the external debug interface is certainly more than powerful enough to do any sort of kernel debugging that we might be interested in. It's definitely capable of setting breakpoints and watch points, single-stepping execution, executing arbitrary instructions, poking at memory, all this sort of stuff. So the idea for my attack was we have these debugging registers. We can do things like single stepping, and we know that we can halt execution in the reset vector. So I basically decided I would try to use the external debug interface to single step the reset vector. And then once the reset vector is about to execute the KTRR lockdown instructions, just jump over that piece of code so KTRR never gets initialized. So if we look at the reset vector, we'll just step through all of the first instructions. And then once we see that we've hit this conditional branch where we're just about to start doing the KTRR register initialization, set x17 to 0, jump over the KTRR code altogether. Now, this is a nice idea, but we don't actually have all the tools yet necessary in order to carry it out. We know that we can halt a CPU, and we know that we can execute arbitrary instructions on it and do things like modify the values in registers. But we haven't yet found the ability to resume executing on the CPU after it's been halted. So if we set a breakpoint on the reset vector, for example, that's nice, but it's not going to be of much use if we can't continue execution after that point. Furthermore, there's another somewhat more subtle issue, which is that we're using one CPU to hijack another CPU as it resets. But CPU resets happen all the time. Anytime a CPU core is idle for a couple of seconds, it'll eventually just do a reset as it powers down and powers back up again. So we're going to have to do this KTRR hijack. We're going to need to modify the execution of the reset vector and skip the KTRR initialization every single time that a CPU core resets, unless we can find some way to disable the core from resetting. So I didn't know how to do either of these two things. So I kind of just decided to play around with that original proprietary register that I'd found earlier. So the XNU source code documents a couple of the bits. I think it documents 2 of the bits in that register. The remaining bits are undocumented. So I figured, might as well set some bits, clear some bits, see what happens, see if I learn anything interesting. And I kid you not, by sheer dumb luck, it happened that that register contained exactly the pieces of functionality we needed to pull this hijack together. So bit 30 actually will clear the halt, and it'll allow the CPU to resume executing. And bit 26 will keep the CPU powered up so that it doesn't subsequently reset, and then we have to re-hijack the reset vector. So basically, the attack that we described before works perfectly well once we have this new functionality. We just make sure that once we hit this branch, we skip over the KTRR register lockdown code, and then these registers never get written to, KTRR is never initialized on the system, and kernel memory becomes executable. So what this looks like is first we have KTRR enabled. Once we do this hijack, KTRR is disabled on the MMU, and now any page in kernel memory could now potentially be executed. Got a little bit more to go. Thank you. So now that we